Hello everyone, welcome to the OneClass channel and good evening. My name is Fajori Rome and I'm an Honors Bachelor of Science graduate currently working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some extra homework help or some tutoring, please check out the links in the description below. We're more than willing to help you. Alright, so now with that being said, let's switch over to our first question of the evening. We have question 1 being, does carbon tetrafluoride have a polar bond? So, as the question indicates, yes, we will start this question by first completing its Lewis structure. For that, we would need to actually know, give me a quick second actually here, almost forgot to actually create these tabs so that way we can actually continue on. But as I am creating these tabs, just be wary that we are going to be creating the Lewis structure for carbon tetrachloride. Tetrafluoride, tetrafluoride. I think I wrote the wrong thing down. CF4, sorry about that. CF4 is carbon tetrafluoride. Oh no, looks like we've lost one of our files that we can use. That's okay. We have these. And sorry, we're just gonna take a quick there we go, that's the last tab we need. And now let's continue on with the question. Carbon tetrafluoride, does it have a polar bond? So let's first draw out, as I said, the little structure. For that we need to know how many electrons we're dealing with. So with carbon, okay, we're always going to be reviewing our electron configuration here, just because that's always a commonly asked question. So carbon starts with helium, okay, and then it moves on to 2s2 2p2. The reason why I'm not going too in depth in this is just because that's not really the focus of this question. We just want to keep getting down our electron configuration for these type of molecules. So fluorine being the 9th element here, it'll just start with helium, but we have 2s2 2p5. The reason why I did this is because this is the other way of seeing the amount of electrons in the valence shell there are. So with this being said, we're dealing with 4 electrons for carbon and 7 electrons. See how I added these numbers together? So the suffix over there, those are what you'd add together. So with that being said, we have 4 fluorines. So it'll be 7 times 4. So in total this will be 28 plus the original 4 from carbon. And so we need 32 electrons in the Lewis dot diagram. So let's start drawing it out. Carbon will be in our middle because that is the only different one. And so we just draw out at least the first bond of each one, and then we add the fluorine on each side. So now we have carbon tetrafluoride. Please don't forget your actual valence electrons. The reason why I know that fluorine has this much is because if you count it, fluorine still needs to, based on the 7, share 6 more, because right now it's only sharing 1. So when you do the 6, it forms a perfect shell like that. Same with this fluorine, same with this fluorine, same with this fluorine over here. And if you actually count them out, you would see that you actually have 32 electrons, because it would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So it's perfect. And if you did your electron number as well, you'd also see that carbon is completely satisfied because it typically has 4 in its valence electron. Subtract how many does it have now by itself? 0. How many is it sharing? 8, because it's sharing divided by 2, and you do indeed get 0. So carbon is completely satisfied. You should always be getting 0 because, as you see here, carbon tetrafluoride is a molecule with no charge. So theoretically, now when we try the fluorine, okay, typically 1,7, it has 6 by itself, okay, and it's sharing 2 of them with that carbon. So 6 plus 1, that's equal 7 as well. So this is perfect. So all these are perfectly balanced out for carbon tetrafluoride. So what does that mean? Now we can actually say what type of shape it is. This is all tying into whether we have a polar bond or not. We kind of want to see how we're working with in regards to how it's being pulled. So based on this shape, all right, we have 4 things attached to carbon, which I do have in a different color actually. So 4 things attached to the carbon, 2, 3, 4. So it has an electron, not number, it has electron pair geometry number of 4, meaning this will be tetrahedral. And because none of these 4 things attached to it are lone pairs, it's also going to be tetrahedral shape for its molecular geometry. The reason this means actually that carbon is going to be perfectly pulled by each side, perfectly pulled from each side by the fluorines. So we have this and this. Think of it going in and out of the page, but pretty much this is what we have as a bond. It kind of forms a perfect it's hard to explain really. It's kind of forming like a perfect if I were to draw, it's kind of like a little triangle with like a point up here. So it's like that is the kind of the shape it's forming, if that makes sense. This is what they mean by tetrahedral. Yeah, it's a little bit tricky to try to explain in words, but this is kind of like the shape. 1, 2, 3, 4. So you see like that, and the carbon is smack dab in the middle of all that. So because they form that shape is in a sense perfectly stable and wants to be pulling equally at each side. So this actually is a non-polar molecule because every fluorine is pulling equally. But that does not answer what type of bond you actually have. We've done all this to give you a picture of the molecule, but when you actually want to deal with the bond itself, you have to look at something else, the electronegativity. The reason why we did this first, because it all ties in together. If you see, sometimes they'll ask you if you have a polar versus non-polar molecule instead of just a bond. So to understand that, you need to both understand how the molecule itself works and the bond itself work. So now we'll address the bond itself. So for that, we need the electronegativity. So fluorine, right, is quite electronegative. It has 3.98 for its electronegativity. That's fluorine. Carbon is a lot less. It has 2.55. So if we were to subtract these together, 3.98 minus 2.55, the difference, okay, which is 1.43, tells us what type of bond it is, whether it's polar or non-polar. So with that being said, the cutoffs, and I'll just say this because there's a little bit more complexity to it, but between 0 and 0.4, that is going to be a non-polar. And between 0.4 to 1.6, this is now a polar bond. And between 2.0 to whatever number you can get, 2.0 and greater. So I'll actually just do this. That'd be easier. Less than 0.4, greater than 2.0. Oops, I think I did that wrong. Yeah, greater than 2.0. Okay. X is less than 0.4. X is greater than 2.0. That's an ionic bond. Now, what's the caveat here? You're probably wondering what happens between 1.6 and 2.0. If it's bonded with a metal, like a metal and a non-metal, even though it's not 2.0, it still counts as an ionic bond. If it's between two nonmetals, it's going to be a polar covalent bond. Okay, so now with that being said, we have a 1.43, and last time I checked, carbon and fluorine are both nonpolar molecules. Are both nonmetals. Sorry about that. So because they're both nonmetals, this bond right here is going to be a polar covalent bond. So now you see what happened here? We have polar covalent bonds, but because each fluorine is pulling exactly the same on the carbon, it all cancels out to where we end up with a nonpolar molecule. But this question is asking for the bond, so we could have just skipped straight to the electronegativity. I want to give you a whole full picture of it, because I don't want you to assume where it's like, oh, if it has polar bonds, it means it has it's a polar molecule. That's not always the case, just as this example here. So with that being said, let's check it out. So they show all the CF bonds are polar bonds, perfect. And because fluorine is more electronegative, that is true. But although all the bonds are polar, the molecule is not a polar molecule because all the dipole momentum cancels out. So does it have a CF? Does carbon tetrafluoride have a CF bond? I mean a polar bond? Yes. This is correct. But is it a polar molecule, as it also says there? No. So with that, let's move on to the question.